Hi everyone, welcome back. So we've been discussing the era of experience paper and we stopped right where we were discussing the AlphaFold. So we'll just jump back in and just resume where we stopped, right? So we saw that what AlphaFold is doing, it's basically predicting the given 3D structure of a protein given its 1D sequence, right? So what it did was initially for a given protein sequence, how the training was for AlphaFold, which won the Nobel Prize, is it again started with the supervised human learning component again. So, like we saw in the alpha proof examples, it was given a set of input and output. So, a given set of single dimensional amino acids, what is the relevant structure? And this is quite expensive to do. You need to use advanced equipments, X-ray, crystallography, and all that. And it takes time. But it was the foundation of how AlphaFold was created. So 170,000 protein structures to train in the supervised learning phase, right? And then this was given so that to train the model given a given amino acid sequence, what is the 3D structure, right? So here is an example of a protein called lysozyme. So the sequence is this, and it finds a 3D structure for that, right? But this alone wasn't enough. What helped AlphaFold achieve that breakthrough in getting such a high accuracy, which researchers in the field of biomolecules appreciate, and it's the reason for its high accuracy is its depth of quality data that it had. And how did it do that? Like initially, it had access to the PDB dataset, protein data bank dataset, but now AlphaFold did something unique where it used the hints provided by Mother Nature itself, like how Mother Nature has designed these proteins in all different species, tells a lot when it comes to predicting the structure, right? So the example, the case of lysosome protein, it exists not just only in humans, it exists in chickens, it exists in mice, fish. And what the scientists did is it took the sequences of proteins in these different organisms and kind of analyzed it, right? And that helped it get millions of that helped it get a lot of relational quality information, right? So here, imagine the lysozyme protein in chicken. This is how it is in mouse, in humans, right? And then it developed something called what is called a multi-sequence alignment, which is a table where each row of each row is used to represent the lysosome in different organisms. And then it kind of derives these intricate insights from what Mother Nature has provided, right? So from these different MSAs, we can see that if a position is identical across all species, like KVF here, it's identical in all the four, it's probably critical for a function on structure, right? Maybe in the 3D structure of things, these three individual molecules, KVF, can be close to each other, right? Or it's like if two positions always change together, like here we see position 4 is G and position 11 is always A. These amino acids might be physically close, right? And one more thing could be like it's like nature, Mother Nature is giving us a hint, right? So nature has already tested which combinations of amino acids work together in a protein, right? So by the sheer depth of understanding, just by the sheer richness of the quality of data, AlphaFold was created, and it is performing so well. The predictions that are there have a remarkable level of accuracy and is being used by the scientific community throughout the world, right? So without the power of Mother Nature, AlphaFold would have just access to the PDB dataset and it would have predicted something which would have been correct, but adding this nature spice, what we call it, just changed everything, right? So what we saw here, like there's also this side of reinforcement learning where you learn from experience, but so does the depth of understanding. Here we see in the example of AlphaFold, just by the power of quality information and just through supervised learning, you could create something truly novel, right? So I want to focus on this point a bit more, and we look at just one more example, which is something called Halicin. So Halicin was an antibiotic developed by MIT researchers, and it was purely based on supervised learning. And so here you see in this paper, a deep learning model intensifies a powerful new drug that can kill many species of antibiotic-resistant bacteria. So the story of Halicin goes like Halicin already existed before, mind you. I'll tell you that it was used. I think it was tested to use in the data set to treat diabetes. but now it was discovered that it can even treat antibiotics as well. So how was Halicin trained? So basically they used a deep neural network, basically a graph neural network. So I've already made a video on GNNs in my my video on DoDash. So if you want, you can check it out. So how DoDash, how GNNs work. So the training set, it had close to 2,500 molecules with known antibacterial activity against this particular bacteria called E. coli. So break it down. Input could be your series of molecules, and output could be the probability that it can handle E. coli, the probability to kill E. coli. So one could be halicin could be 0.9, some other molecule could be 0.5. So what it did is, during its training phase, it kind of understood what it takes for a particular molecule to kill E. coli, right? What functional groups, what structure, what torsion angles, what overall, what it takes for a molecule to be resistant to antibiotics, right? So here, just by pure learning through human data, no learning from experience, it found out that halicin can treat antibiotics as well, right? So here, as we saw in the AlphaFold example, pattern recognition at scale, pattern recognition just by the sheer depth of understanding, pattern recognition just by the richness of your data, can lead impactful results and can also discover something truly novel, right? So yeah, here's this one more example that I wanted to point out. And again, I want to go back to this section of the paper, to achieve, and it says to achieve superhuman intelligence, it will be predominantly from experience. But as we saw in this example, the level of the impact human data has, because in all the three examples that we saw here, you can see the supervised learning component was always there. It was always there, right? So it's not like you can completely omit out the learning from supervised learning, because like to discover something novel, there should be some foundation, right? And that's what supervised learning provides. Sure, there are examples like AlphaZero, which didn't have any supervised learning component. It was just pure reinforcement learning from experience. The model where you just provided what are the overall steps, and then the model was playing the game, and then it learned what all possible steps could be there. But here we see wherever there are matters related to us humans, where human lives are at stakes, where we saw a drug discovery is at stake, which is so relevant to humans, right? Or discovering a new chemical material altogether. That will always I've seen in the examples that I saw, that always has a supervised learning component, because in the initial training phase, the model should understand, right, what it takes for a structure to be a good material, right? So let me just jump back to the PDF. I had some interesting points on this regard that I wanted to share. So yeah, here in the paper, clearly it was hinting towards human data is tapping out, right? Where we saw in the first part, era of human data, it said things like the majority of high data sources have already been used. The pace of progress driven solely by supervised learning is demonstrably slowing. Valuable new insights lie beyond the current boundaries of human understanding. But it's not like the paper is screaming out that, oh no, reinforcement learning is the way. The paper also acknowledges, as we'll see in the sections, that experience and human data are not exact opposites, or a small amount of human data may facilitate a large amount of autonomous learning. And this we'll see that the paper actually says this, right? So let me just go back to the paper where it said the points, I think, yeah. Here you see experience and human data are not always opposites. In this way, a small amount of human data may facilitate a large amount of autonomous learning. So that's the whole point, right? It's not like human data is going away anywhere. Human data kind of complements, like, right? A good topping on your pizza. That's what human data is like. And both of them together will shape the future of superhuman intelligence, right? Of course, RL agents can advance to a new level, which I don't know, where it might not rely anything on human data. We don't know what the future look like. But right now in the present, this is the scenario. I've provided you a couple of examples that kind of substantiate what I said, right? So, and also in the case of, as I was talking about, where stakes, like where human lives are at stake, like drug discovery or molecule prediction, right? There, suppose, okay, you use RL agent for that. Okay, there is no supervised learning component, and the RL agent predicts a structure. But then how do you verify if that structure is correct or not? or if a pure RL agent is predicting drugs, right? How do you verify the drug is the correct structure or not, or it can be applied to humans? Human lives are at stake here. You can't just blindly conform to this without having a solid verification point, and that is where supervised learning can come into play. So in the case where it predicts a molecule structure, it will this molecule bind to protein X, requires a binding affinity predictor, which is like the RL agent, suppose, predicted the structure. Now you use to verify that structure, you again use a supervised learning binding affinity predictor, which is nothing but a supervised learning agent which has learned which structure is possible. Maybe check out the overall energy, calculate the potential energy of the structures. But that is again a product of supervised learning. It's a product of humans being in the lab and doing experiments, right? So as we see, as I said, thus human data isn't going anywhere. Most applicable in biology, healthcare, and everywhere. And yeah, I was at this conference, I think last month, where it was related to biomolecules, and there was a debate going on that is the era of wet lab experiments over? And there was a very senior faculty. She said that no, it's not over. Initially I didn't pay. I was not sure, but right now, like from the knowledge that I've had and from what I've seen, wet lab experiments will continue to play an important part, because suppose a scientist, a RL agent predicts a molecule, who's going to verify that molecule, right? Or because we saw in the case of even AlphaFold, how was it trained? Protein data bank. And how did protein data bank come into existence? It was by humans in the lab doing experiments using those X-ray crystallography to actually see if that structure makes sense. So yeah, here we see again one more thing, that pure learning through reinforcement learning, along with the use of reinforcement learning, along with supervised learning components, will be the future of superhuman intelligence. So we'll be continuing the next part.